Hey guys, happy 4th of July. So I'll explain this in the an announcement to you guys, but obviously the university is closed tomorrow, but we have material that needs to be covered because of holidays. We've missed 2 days, whatever. Anyway, I decided I'm just going to record it and then you guys can enjoy your 4th of July. And then we'll yeah, see you next week. All right, so the first question, this is going to be the review of chapter 10 on acids and bases. So this first one is with the Bronsted-Lowry acid, it's a proton donor. Which of the following components is not going to be a Bronsted-Lowry acid? So let's see if I can get my little doodad to work. There we go. Okay, so just to remember by definition, um, let's see, water is a base, the conjugate base is left over, and after the proton has left, um, when we're talking like, oops, sorry, let me back up. So when we're talking about answer A, okay, which is not the correct answer, but this one is the water is going to be a base. So the conjugate base is left over after the proton is lost. So HBr is going to turn into like a Br minus, right? NH4 plus, this is a base because the N has a lone pair that's capable of accepting a positive, right? And so the NH4 plus does not have it in a lone pair, and therefore it cannot accept a hydrogen. So B is out. For C, H3PO4, this is a strong acid that has a conjugate base that is a weak acid when it's combined in and of itself. So this one is not the correct answer. So the correct answer is going to be answer D, um, because the OH here is going to accept the proton from the acids, and then it's going to be forming hydrogen. So basically, you're going to have a hydrogen plus the OH or the hydroxyl group, and then this is going to combine together to make you water. So this one is not going to be a Bronsted-Lowry acid. Okay. So for this one, what you want to do is go and look on page 331. Okay, so let me put this here. Page 331. And you're going to be looking at that chart, which is chart 10.3 on the strength of acids. And so basically when we're looking at these and we look at the strength of them and whatnot, on table 10.3, KNO2 is going to, or I'm sorry, HNO2 is going to turn into NO2. H2SO4 is going to turn into HSO4 minus. HCl is going to turn into chloride right here, right? And so when we look at that chart, we know that HCl is strong. Okay, so HCl is strong. H2SO4 is strong, but HNO2 is weak. Weak, I can spell. All right, so therefore, with knowing that and comparing all of them, then that means that answer A is going to be the correct one. Okay, because again, we have to know which ones are strong and weak, and by looking at that table, we know that the HNO2 right here, this guy is weak. Okay, for this one, use the ion product of water to calculate the OH concentration for an aqueous solution of H3 or H3O plus of a 6.1 times 10 to the minus 4 molar. Okay, so with this one, remember, and again, this is in your book, the formula. So KW equals H3O plus times OH minus. So then when we rearrange that to solve for OH, what we end up getting is OH is KW over H3O plus. And the standard for KW is that it's 1.0 times 10 to the minus 14. So then when we plug all of this in, we know that OH equals 1.0 times 10 to the minus 14 from right over here. That over what we have in this equation right here. Okay, so 6.1 times 10 to the minus 4 molar. So then when you work that out, that's 1 over 6.1, and that ends up being 0.1639. And then when you do the decimal places, right? So when we have, so for decimals, let me put this over here. I'm running out of screen. Decimals, we have minus 14 plus minus 4, and that gives us minus 10, right? So the minus 14 is from here, the minus 4 right there, and that gives us minus 10 as a net. So then this would be 0.1639 times 10 to the minus 10, and then when we adjust the decimal point again, then that we have to change it one more time. So that ends up giving us 1.6 times 10 to the minus 11 molar. Okay, because again, this is minus 10, and we have to change this decimal point one more time. So then that ends up making it minus 11. Okay. Which of the following solutions is not acidic? So remember that acids are below 7, pH is 7. So if we're acidic, that's below 7. And then if we're basic, otherwise known as alkaline, then that's going to be above 7. So 0 to 7 is acidic, 7 to 14 is basic. Okay, so looking at this, this is going to be acidic. This one's going to be acidic. This one's going to be acidic. Our blood pH, fun fact that you guys all probably know, is actually slightly basic, because if pH 7 is neutral and our blood is around 7.4, then we actually are a little basic. So, good job. All right. Let's see. Which of the following is a buffer system? So remember that a buffer requires a weak acid and a salt containing its conjugate base. All right, so let me write this down for you guys. All right, so a buffer requires a weak acid and a salt containing its conjugate base. All right, so looking at these answers, NaOH and NaCl, this is not a buffer because a solution of a strong base and a salt are completely ionized. So A is out. B, KCl and NaCl, these are both salts. So the mixture has no weak acid present, and so it's not a buffer. So that one's out. C, this one is the correct answer because HF is a weak acid, and then the salt, so HF is a weak acid, and the KF is a salt. So the mixture of KF and oh my gosh, HF and KF is going to be a buffer, so that is the correct answer. D is not the correct answer because CaOH2 is a strong base. Okay. All right. Right. This one is, which of the following is not a conjugate acid-base pair? So remember that the definition of conjugate acid-base pair is that an acid and a base that differ by one hydrogen. So when an acid donates an H plus, the product is a conjugate base, which is capable of accepting an H plus in ion in the reverse reaction. All right, so let me write that down. So the definition is of a conjugate acid base pair is that an acid and a base that differ by one H plus. All right, so then when we look at all of these guys, the correct answer is going to be B here, because the B will not lose H plus. Okay, it lost an O2. Okay. All right. Which of the following a uh, is the weak acid nitrous acid? All right. So this one you have to pay attention to the NO4, NO3, NO2, and NO. So HNO4, this is peroxynitric nitric acid. HNO3 is nitric acid. And when you look at that chart, this is strong. Okay, right now we're looking for weak. HNO2 is nitrous acid. And this one is weak. And then we have HNO, and this is nitroxyl. And this is a gas intermediate. So because of this, we're looking for a weak acid. The only one that's going to be weak is going to be answer C here. All right, so for this one, we're looking for the conjugate base in this following equation. So again, a little bit of housekeeping. If we lose an H plus, then that's going to be acidic. If we gain an H plus, that's going to be basic. Okay. So with that, we know that we are going to, I'm looking at the, hold on a second. Sorry, I could feel a sneezing fit coming on, and I didn't want to sneeze on camera. Okay, so what we're going to be doing again, remembering, is losing hydrogen is going to make it acidic, but if it gains it, it's going to be a basic. So when we look at this equation, right, this separates, right, and then it ends up being that the chloride, instead of being like neutral, it's going to be gaining that one hydrogen, right? And so that makes it C going to be the right answer. Okay. So because uh when it was balanced out here, it was great. And then you take away the hydrogen, and then it ends up having that negative charge, and then that's going to be what your conjugate base was. So again, remember that if you lose a hydrogen, it's acidic. If you gain a hydrogen, it's a basic. Here's another kind of fun formula. So if you have, for instance, HA plus H2O, this is a reversible reaction. That would make it H3O plus plus an A minus. So the HA would be your acid, and this A minus would be a base. If you flip-flop it and go the other way, then you know that an A minus plus an H2O, this is just an example to try to explain it a little bit more. When those combine, you would end up being HA plus OH minus. So your HA would be your acid, your A minus would be your base. Okay, so your base is going to be gaining that hydrogen. So again, the correct answer is chlorine. Okay, so which of the following acids is a strong acid? Also, just to go back to this last question for a second, there's a table of your common Bronsted-Lowry acids and bases too, and so you can see that a common base is going to be your chlorine, and that's in your book too. So if you were lost still, even though the formula and all that stuff and gain and lost, there is a chart that you can refer back to. Okay, so which of the following is a strong acid? So looking at, again, your book has a beautiful chart of different strong acids and bases. So, so basically, if you go through all of these, wait, how did sorry, I was stuck on that one. Okay, sorry. Okay, so your strong acids, there's going to be hydroic acid, hydrobromic acid, perchloric acid, hydrochloric acid, sulfuric acid, nitric acid, and hydronium ion. Those are all listed in a table of which ones are going to be like your strong acids. And so the strong one on this list is going to be HBr, which is hydrobromic acid, and this is on that list of strong acids that's in your book. Nitrous acid down here, this is a weak one, and so is phosphoric acid. He's pretty weak. And then HCN is hydrocyanic acid, and he's also weak. So this is weak, 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 and this one is strong. And again, that's from a list in your book. Okay. Okay. So this one, the OH of a solution is 3.6 times 10 to the minus 4. What is the corresponding H3O plus? So basically, if we do a couple definitions here, so the H3O plus is going to be your conjugate acid, and your OH minus, just remember, is going to be your conjugate base. So if you take and you look at table, this is like super important. Table 3, the table is on page 339. Okay. Basically what we have to do is calculate the KW first. So if you take 1.0 times 10 to the minus 7 for your acid, and then you times that by 1.0 times 10 to the minus 7, which is your base, you end up getting your KW of 1.0 times 10 to the minus 14. Okay, and remember that your KW is going to be your water dissociation expression. So what we're going to do is we have your formula of so KW equals H3O plus times OH minus. And then if you solve for your H3O plus, then that ends up giving you the formula of KW over OH minus. So when we plug in these numbers using this formula right here, okay, we have your H3O is going to be 1.0 times 10 to the minus 14, and that came from right here, okay? And then that over 3.6 times 10 to the minus 4, and that comes from right here, okay? And then when you do all of those things, it ends up being 1 divided by 3.6 is 0.277. And then when you do the numbers, 14 minus 4 ends up giving you minus 10. And then you have to shift that decimal point a little bit more so that we can make this a whole number. So then you end up getting 2.77, right? And then you round that up because of significant figures to 2.8. And so then when you get all of your numbers correct, because remember when we moved that decimal point one more, we added one. So this is 10 to the minus 11th now. So the correct answer again is 2.6 times 10 to the minus 11 moles. So again, looking at that table, first we had to calculate kW by taking the acid times the base, and we ended up equating that to minus 14. And just a reminder that that kW is the water dissociation expression, and then this is the formula for kW, but we had the kW and we had the OH, so we wanted to solve it for H3O+, so we rearranged the formula to H3O+ is equal to kW over OH. And then when we plugged our numbers in from the formula that we calculated as well as from the question, we end up getting that when we adjusted for sig figs. Okay, the H3O plus of a solution is 6.7 times 10 to the minus 8 molars. What is the pH of the solution? So, what we're going to do is remember that pH is negative log of the H3O plus. And so what we're going to do then is calculate that. So the pH is going to be the negative log of 6.7 times 10 to the minus 8, which we got from right here. Okay. And when you calculate all of that on your calculator, that ends up being 7.17. Ta-da. All right. Given, this is the last question. Okay, given the following equilibrium between hemoglobin, oxygen, and oxyhemoglobin, according to Le Chatelier's principle, increasing the amount of oxygen in the blood will result in what? So basically, Le Chatelier's law there is going to be when a stress is placed on a system at equilibrium, the system shifts to relieve that stress. And so what we're going to have to do is when we increase the amount of oxygen in the blood, you are going to do two things. The increase of oxygen is going to cause you to have an increase in the amount of oxyhemoglobin so that it can carry it. And then also it will decrease the amount of hemoglobin in the blood. So they have to equalize out. And therefore, since B and C are both the correct answer, D is going to be the answer for this question. All right, cool. Well, thank you for coming, and I will get these out to you guys shortly because you don't even know it's coming. All right, thanks, guys, and I'll do the review next. Thanks.